Hey, what's up, guys? This is Cheng here. So today, let's take a look at one Codeforces problem, ice cave. Okay, so you're playing a computer games, and then you're given like a 2D board, like n by m boards, where there are like several ice on top of it, and the ice has two status. Basically, it's either a dot, right, or an X, where dot means it's an intact ice, and X means it's a cracked ice, right? And you can move from one ice to another, right? And so every time, so the rule is followed is below. Basically, every time if you step on an intact ice, that intact ice, basically a dot, will become to an X, which is a cracked ice. And when you stepped on a, a cracked ice, you fall, right? That's basically the rule. And there's a special rule here. So due to some limitations of the game in engine, you cannot jump on the same place. Basically, let's say there's a dot here, right? So if you move to this dot, right, and then this dot becomes an X. So and if you want to fall from this cells, you cannot jump again on the same cell, which means you have to move somewhere else. Move somewhere else, either on either direction, right? And then you can only then you can move back. Okay. And the goal is like this. Basically, you're given like a starting point and an ending point. So which means you start from this R1 C1 cell. And at the beginning, this cell is cracked. It's guaranteed to be cracked because you have just fallen here from a higher level, right? And our target is to fall, basically to fall down through this target cell, which is R2 and C2. And we just need to return either yes or no. So yes means we can fall from this target cell. No means we can't. And the size of the board is like 500, right? And here are some examples, right? So for example, we have like 4 by 6 boards, right? So here we have a bunch of like the ice, right? So we have a bunch of intact ice, we also have like a bunch of like cracked ice. So in this case, the starting point is 1/6, which is this one, right? So starting, and it's a one base, right? So we're starting from here, and the target is 2, which is this one, which is here, right? And the answer is yes, because so one of the observations that so in order to fall from here, we have to somehow get here, right? And we cannot walk on the cracked ice because the moment we step on the cracked ice, we'll fall from there. So which means that we can only go follow go use those intact ice, which means we'll go down, right? And then we'll go left, and then we go up, and then finally we'll reach here. And when we reach the dot here, we cannot fall, right? We cannot fall from here because the first time we step on this target cell, it will become a cracked ice, which means we have to either go up or go left, and then we come back, and then that's when we can fall from here, and that's why we need to we return yes, because we can fall from there. And the second example is this one. So we have 5 by 4 boards, and the starting point is 5, 3, which is this one, right? And the ending point, the target is this one. It's the top left corner, right? So in this case, the answer is no. And why is that? Because even though we can reach that target, the moment we reach that, it will become like X, right? But after that, there's no way we can move somewhere else, right? Why is that? Because we have this one. We have a dot. We have a X dot dot, and then we have a dot 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 x, right? Since for this dot, there's only one another dot as a neighbor, so the only way we can get to this target is it's coming from here, right? So the moment so we need to step on this one first, which means this one will become an x as cracked ice, and then we can get to here. But the moment we step on this ice here, all the neighbors, they are all the cracked ice. So which means that we cannot move to another place, and which means we cannot fall from here, because if we either move to the right or down, we'll fall from this one or from this one, right? Yeah, and I think that's the description or statement of this problem. This one obviously it's like it's a traverse problem. We should either do a DFS or BFS traverse, but there are like a few scenarios we need to consider. So let's see, we can draw some. I think there are like 3 examples here. Sorry, 3 scenarios here, right? So the first one is the start and the end, right? The start and end are the same cell, right? This is also possible because the start and the end, they could be anywhere. So for this one, if the start and the end are the same cell, so what's going to be the condition to return true, right? So first, if the start and so at first, the start is always a cracked ice. So which means that let's say we start from here, right? We start from here. This is going to be our starting point, right? So like I said, in order to fall from the starting point, so the condition is that at least one of the neighbor has to be a dot, right? Otherwise, we cannot even move. As long as, at least, right, one neighbor is a dot, right? Because as long as there is one neighbor is a dot, we can move to that place and then we can come back, right? And the second scenario is what? Is the of course is the as starting and ending point is not the same cell, right? So the ending point is a cracked ice. It's x. So second scenario is if the target or is a x. This one is a little bit easier. We just need to check if there's a path. If there's a path from S to E, right? From start to end. Because as long as we can find a path. So when I say the path, I mean that there's a path like consists of dot, right? I mean because when we trying to walk on the ice, we cannot walk on the cracked ice because we'll definitely fall from there, right? So if the end is x, all we need to check is that if there is a path from start to end, and then we know, okay, the answer is yes, right? And then the last one is that the edge, the end is dot, right? Right. So if the end is a dot, right? So what does it mean? It means that we have to. So first, we also need to check if there's a path from start to the end, right? And the second one is that we need a 2 plus what? 2 plus at least 2 neighbor, are dot, right? So that's going to be the second conditions if the end is a dot, because if this end is a dot, like I said, we have to first, we need a dot to be able to reach here, right? And then we need a second dot to be able to walk back, so that we can fall from this target, from this end, the end cell. Yeah, so that's basically all the scenarios here. Of course, we can simply just check these three scenarios one by one. That will definitely work, right? But I think, but the reality is that actually we can combine all the three scenarios into one unified like logic, which is what? Which is every time when we walk on when we visit like a path, right? Visit a cell, we will mark that cell from dot to x, and the exceeding the end determinate condition is that whenever one of the neighbor, whenever we see like the end point is a cracked ice, right? Then that's when we will return true. Otherwise, we'll return false. So let's say let's take a look at that, right? So let's say, I mean, when I say it's going to be the next, basically, if the next cell, not including the starting point, if the next cell is a end, is the end cell, and the status of the end cell is a cracked ice, then we return true. So let's verify that logic one by one, right? So for this one, for the first one, if the s and the n, start and end are the same, right? So first we will need to go somewhere else, right? So let's say we have a neighbor which is a dot, right? And then we can reach that. We can reach this one, and at this moment, this one will become an x, right? And then basically, and this cell will be pushed into the queue, right, or a stack. And the next time, right? So the next time when we are processing, when we pop out this cell from the queue, then one of the cell, the neighbor is this one. It's end, which is the a cracked ice, and then we just return true. So which means the first scenario uh, works, right? I mean, if the starting and end point are the same cell and there's no neighbor, I mean, which is a dot, then we'll certainly return false, because we cannot find the next number, right? The next cell, which is the end point. And for the second one, right? For the second one, it's also kind of straightforward, because every time when we mark the dot to x, we'll finally reach the end point as we'll finally reach the end point. And the moment we see an end point, okay, it's an x, right? Then we'll definitely return true in that case. Then how about the third scenario, right? So the third scenario is a dot. So will our logic also work for that? So let's try an example. Let's say we have this one x, 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 and this is a dot, and we have a dot here. Okay, right. So let's say maybe a few dots here. So this is the end. Let's say this is the end point, and here's the starting point. This is the starting point. This is the end point. Both of them are a dot, right? So in this case, uh, we can see that the end point has two neighbor, which are a dot, right? And then there is a path from the start to end. So which means the third one should return true. So if we use our logic, right? I mean, every time when we visit like a cell, we mark the cell to x. So which means that it doesn't really matter how we in which sequence we traverse those dots. So this two, right? Basically, this two cell could be marked as X, right? But they're following a sequence, right? So let's say there's a time. Let's say if this one is a current has been traversed, right? And then the next one is a dot, right? So the moment we see a dot here, we always mark it to X. So no matter in which sequence we traverse the dot here, there has to be a time that the target or the end cell will be marked to X, right? And then there will be and then once that one marked to X, the second cell will be processed regardless, which is this one, right? So when this one got processed, when we process this one, we see okay, one of the neighbor is the end point, and then it's which has like a cracked ice. That's when we return true, right? Basically, as you guys can see, so regardless, in which sequence these two neighbors are processed, either one of them will be processed first, right? And then when that happens, the end cell will be marked to X, and then when the second one got processed, it will meet our condition, and that's when we will return true. Cool. So I mean, in summary, which means that we can just use that one logic to handle all the three scenarios. And with that being said, let's start coding. Okay. So we have few parameters. We have an n, we have an m, and then we have r1 c1, r2 c2, and the size is 500. And we also need like a 2D array to store the board, right? Cool. So mm, so this one is gonna be a 500 plus 5, right? It's gonna be a 505. And then we need a bunch of like integer. We have n, we have m, we have r1, c1, we have r2, c2, right? And then we also need like a 2D board to store the ice. Since it's a string, it's a char, right? I'm going to use a char 2D array here. Okay, and then the first, let's read those parameters in, right? We have n and m, and I'm going to read through the board, right? So we start from one, since it's one base, right? N I plus plus, right? And then we have J1, J, M, J plus plus, right? And then we have maybe read this C in I and J. Okay, right. So that's how we read the board. And then the next one is that the starting point and ending point, which is R1, C1, R2, and C2, right? And then to do the traverse, we can I'm using a queue here basically. In C++, I'm using a DQ, and in the DQ basically I'm using a pair inside the queue because we need to store the coordinates, right? So we have int, and then we have a queue, right? So at the beginning, I'm going to push the starting point, right, to the queue, which is the R1, C1, okay, and then for the directions, right? So for the directions, we in C++, let's do a vector of pair, right? And then directions. We have 1, 0, right? And then the minus 1, 0, and then 0, 1, and 0, minus 1, right? So now the while loop, right? So while the queue is not empty, right? then we do the BFS, or DFS. So first I pop the current, right? Gonna be an int of current, so q dot front, right? Oh, sorry, it's not a pop, right? So in C++, there's no pop. We have to do a front, and then we do a second time we do a pop, right? We pop front, and then we have I equals to the current dot first, right? And then int j equals to current dot second, right? So for 4 directions, right? Let's do this. For auto d, right? And then we have directions. We have a new I equals to I plus directions dot first, right? And then we have a new j equals to j dot direction dot second, okay? And then we do the check, right? So basically, if the new I and new j are in the range, right? New I and new I is smaller than n, and same thing for the new j, right? Okay. And then we do this, right? So if the since we're doing the neighbors here, because the reason we do a check here is because if the start and end time start and end cell are the same place, we want to check the neighbors, right? Because that will be because since we cannot jump on the same cell, so that's why we check if the i's of ni of nj, right, is equal to x, right, and then the ni equals to r2, right, and the new j equals to c2, right. This is when we return true, yes, right. Then we simply return here, right, because we don't want to check here, because if, like I said, if we check these things here by using the I and J here, if the I and J are on the same cell, then we'll have like a wrong answer, because we'll assuming that start place is the final answer, right? That's why I check when we process the neighbor, right? So else if, right? Else if we just continue the traverse, right? So if the i's new I and new j equals to dot, right? Then we just push it. We do q push back, right? Push back the new coordinates, right? New I and new j. We also mark this one to a x, which means it becomes a cracked ice, right? And then in the end, if we never see it like this, we never met these conditions, that's when we need to return the no in this case, right? Yep. Yeah, I think that's basically the solution here. Let's try to run the test case then. So we have this one, right? This one we're expecting yes, right? 4, 6. Okay, seems like we have a bug here, right? I mean, let's see. Oh, here, nm. Okay, so this one we have yes. And how about the other one? So for second one, we should have no, right? Yeah, which is no. How about third one? Third one is yes. Okay. Yep. Which means seems correct. Cool. So I mean the time complexity, right? I think it's pretty straightforward. Time complexity is the m times n, right? Because we are only traversing the worst case scenario. We're traversing each cell uh, once, right? So it's going to be n times n, time complexity. Cool. I think that's it, right, for this problem. It's I think it's kind of a little bit of variation of the standard, the BFS or DFS traverse. We have to consider like three cases, you know, and but in the end we can combine all the three cases into one unified logic, which is as what we have seen before, right? And cool. I think I'll just stop here and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.